Hi-oh! Here we are again. Today we're going to talk about Newton's third law, the law of action and reaction. Newton's third law basically says for every action there's an equal and opposite reaction. Take a look at our hammer. Our hammer hits a nail. There's the action. What's the reaction to that? Does the nail just stand by and do nothing? No. The nail actually hits the hammer back. Think of it this way. If you were to push your little brother and sister, won't you feel them pushing back on you? If you didn't, well, then I guess you didn't push on them. So when we talk about action and reaction forces, realize they always come in pairs. You can't pull on something if there's nothing to pull back on you. You can't push on something if there's nothing to push on. And if you push on something hard, it's going to push on you just as hard. You push harder, it will push harder on you. So what you do is you go up to your brother or sister and you hit them as hard as you can. And then you yell, "Mom, they hit me!" Well, it's true. They did hit you. In fact, they hit you pretty hard, just not in the same places you hit them. A way to figure out what is the action and what is the reaction force is a very simple recipe. If object A acts on B, so action, then we get the reaction. B acts on A. So any type of object you want, any type of collision is what you can actually call it, follows this recipe. A on B, therefore B on A. Well, let's take a look at Wile E. Coyote. He's on a rocket, and the rocket is going forward. Well, the rocket's pushing off something. It might not be obvious how rockets work, but they're actually pushing off their own exhaust. The rocket pushes on the exhaust, there's the action, and the reaction is the exhaust pushes off the rocket, and they go in opposite directions. Remember, A on B, therefore B on A. All right, so A on B, therefore B on A. Boy pushes wall, wall pushes boy. Think about it. If you push back on that wall and it doesn't push on you, you're not going to go forward. I mean, try standing there and pushing on nothing. You won't move at all. Now, go up to the wall and push on it, and you betcha you will get pushed forward or pushed away from it. You ever fire a gun? Yeah, the gun kicks. The gun fires a bullet. Well, that's a no-brainer. That's what you hope will happen. But if you've ever fired a gun, you find that the bullet actually fires the gun backwards. So how do these forces compare? Well, let's take a look. We have two kids holding spring scales, and it shows them currently each pulling with 20 newtons. Do you think it's possible for one to pull with 20 and the other to pull with 10? Well, if you haven't done this in class yet, you will, and you're going to find it's absolutely impossible. The forces are equal and opposite. You can try to pull with a different amount, but you're going to find both spring scales will always say the same thing. So with that in mind, imagine if you're driving down the road and a butterfly hits your windshield. Who exerts the largest force? Your first inclination would be to say, well, the butterfly gets splattered all over the windshield. But in reality, the forces are equal. Why does the butterfly get splattered? Because it changes its velocity very quickly. It does a quick acceleration change, and that has to do with mass. So, see what you learned. Do the tires push harder on the road, or does the road push harder on the tires? of course they're the same. And if you want to go faster, you got to push harder. And of course, the road pushes harder back on you. If it can't, we call that ice. And you don't go anywhere. You can't push on the road. So if you walk across the room, guess what? In order to walk, you actually push the floor backwards. And in return, the floor actually pushes you forward. So we've established that they're equal. They are also opposite. And we know something about vectors, right? This is 10 newtons this way, and we have 10 newtons that way. They should cancel to make 0 newtons. So why don't they cancel? It's a great question. I'm glad you asked. Very simply, when you push on something, you're pushing on something completely separate from you. I'll tell you what, try pushing on something that isn't separate from you, like your own shoulder. Go on, you can do it. Try it. You'll find you can't push yourself down. You cannot push yourself over because you're pushing on yourself. Now try pushing on the wall, and you'll find if you push, really push, you will find you get pushed backwards. So we might say the forces, yes, they're equal and opposite, but when they're on the same object, the forces are internal. They're not external. They'll cancel when they're internal, and you'll get 0. So let's take a look at our picture. You've seen something like this in cartoons. There's an obvious problem here. The fan's attached to the boat. The sail is attached to the boat. The fan is pushing on the sail. Both objects are attached to the boat. It's like you pushing on your own shoulder. Your hand is the fan, and the sail is your shoulder. Real long arm here. Can't push yourself down, just like the fan cannot be attached to the boat. Take the fan off the boat and hold the fan away, and yeah, you can get the boat to go. You might notice, especially with the gun idea, right? The things accelerate at different rates. We have a bullet, and the bullet flies off. The gun flies back, but not quite as much. There's a difference in acceleration. The forces are the same. But you probably noticed the acceleration is different. And that's simply because of the mass. Try imagining pushing off, I don't know, let's pick something really massive. A big semi-truck. It can roll if you can get it to roll, but it has a lot of mass. And if you push on it as hard as you can, you are essentially the bullet. And you get pushed backwards. The truck, because of its huge mass, it gets pushed a little bit, and you might not even notice because the mass difference is so great. So let's put it in the form of a formula. We know the forces are equal, right? The bullet gets pushed as hard as the gun gets pushed. And we know Newton's second law, F equals ma, the sum of the forces, mass times acceleration. Each of these have a mass. Each of these have an acceleration. The gun is very large mass. The bullet is very small. But because these sides have to be equal, kind of like a teeter-totter, got to keep them balanced. The change to make them equal has to be in the acceleration. So each side has to have something that's really big and one thing that's really small. Since the bullet has a small mass, the acceleration must be big. We can see that. And the bigger that mass is, the smaller the acceleration, which makes an interesting idea. A skydiver gets pulled to the earth. Yeah, the skydiver gets pulled down. You can see that. But believe it or not, the earth comes up to meet the skydiver. The forces are the same. But the acceleration is not. Who accelerates who? The answer is, of course, they both accelerate each other. Because of the mass difference, the Earth does not accelerate very much. Big mass, little acceleration. Little mass, big acceleration.